Hello and welcome. Today I'm delighted to show you some of our facilities that we utilize at TNO and TU Delft to make quantum chips. I'll show you how we characterize a quantum chip, and I also show you how we can use such chips in an actual operational quantum computer. Shall we begin? We are now in Kooi Laboratories, or in short, EKL Cleanroom Lab. Everything in this cleanroom is made compatible to process on silicon 4-inch wafers. In that sense, this cleanroom can be looked at as a mini version of any huge semiconductor manufacturing company. In a simple way, we could divide the fabrication process of a quantum chip in 3 stages: material, microfabrication, and nanofabrication. Behind me, you see the tool that we use to make the material that we need in quantum chips. It is actually a reactor with gas inlets and lamps to control the temperature. So what we do is to let the gas sources inside, we set the temperature, the gases react to one another, and form a solid layer of semiconductor on the surface of silicon wafer. With this particular technique, we can deposit nanometric layers of semiconductors in a very precise, controlled way. We also, at this point, do several material characterizations to check the quality of the material and also tune the process for things like thickness and composition. We are standing now next to a lithography tool from ASML. Once we have the material ready, we use this tool in several steps to print down the micrometric structures that we need in quantum chips in a process that is called photolithography. After this, we transfer the wafers to another clean room, where we dice them to smaller pieces and have them ready for the third part of the fabrication, or nanofabrication. We are now outside of Van Leeuwenhoek Laboratories, or in short, VLL. This is where we do the last and most important part of the fabrication. For this part, I asked my colleague, Lara, to show you inside.
After the chips are transferred from other cleanroom here, the next step is to fabricate a quantum chip by using a technique called electron beam lithography. Here, using the same principle as for making the pattern, we can actually image the result of a lithography process, one of the quality control methods we are using in our work. And on this screen, you can see an example of an electron microscope image of a quantum chip. And the feature size on our quantum chip are similar to what you would find on the processing chip inside of your latest generation of smartphone and laptops. And now we have beautiful quantum chip, and we are ready to test its quantum properties.
Now you have seen how we fabricate quantum devices, but we still don't know if they work the way they are intended to. In order to bring out quantum properties of such devices, we need to put them in cold fridges. And I mean very, very cold. James is here to explain more.
So here you can see TNO's first quantum-ready fridge. It's been set up specifically as a test bed to allow us to characterize the quantum properties of our chips. So what we do is, we take our quantum chip, load it into the fridge, and it cools down to -273°C, which is colder than the coldest point in outer space. Once it's cold, we can run our experiments and determine if the chip has the properties that we would like. If it passes our tests, it moves on to the next stage.
Hopefully, some of our chips pass all the characterization tests, and so we can use them to do actual quantum computing. Nodar will tell you more about our quantum computer prototype, or as we call it, Quantum Inspire.
Welcome to Quantum Inspire. This is where we take our quantum chips and turn them into fully functional quantum computers. Classical computers work with bits, which can be 0 or 1. Quantum computers, in contrast, work with quantum bits, or as we call them, qubits, and due to quantum mechanical properties, they can be 0 and 1 at the same time. This allows quantum computers to perform calculations exponentially faster than classical computers. In the years to come, quantum computers are expected to revolutionize a number of industries. All you see in this room is a part of our quantum computer. On this circuit board, we have a quantum chip that is similar to the one inside this fridge. It is going to be our central processing unit. These instruments provide the quantum-to-classical interface. They are used to control the qubits, make them do the computations, and measure the outcome. We have made our quantum computer accessible through cloud, so you can log into quantuminspire.com and try out your own quantum algorithm. happy quantum computing!
So, this is the end of our tour. Everything you saw today is the great work of engineers at TNO, which is mostly done together with the researchers of TU Delft within QTech collaboration. A great team of scientists that are working together to make the future of quantum computing and quantum internet. I hope you enjoyed it. Goodbye and see you around.